Okay, let's start then. So this is Chemical Fields and Diffusion. My name is Pedro Castel. Some people already know me from yesterday. And if we remember that the workshop is live stream, recorded and distributed. So yesterday we built a simulation on cancer. It was cell population dynamics, and we wrote some questions. For example, uh, how to improve the model, how to implement other layers of complexity. One of these layers of complexity would be nutrient consumption. And to model nutrients, for example, in a system, you may want to implement it as a chemical field, which diffuses in space and decays in cells or in medium, can be absorbed, can be secreted by certain cells. So all these behaviors and interactions are extremely powerful here in CompuCell, and you may want to implement them in your simulation if you have to model a diffusive field. So our topics are fields, concentration, gradient, diffusion, the diffusion equation, the boundary conditions for the diffusion equation, in CompuCell 3D, how it's implemented, and I will demonstrate it for you guys using the CompuCell 3D implementation of diffusion fields. So what are fields? Fields are a quantity that exists both in space and time. So this is very, very generic and simple at the same time. So you can have a delimited space and a delimited time. So for example, if I take a cup of water, I have a limited space. If I drop a dye here in the water, the dye will spread. It's confined in the inside the cup, and it's also confined in time. So for example, before I drop the dye, there is no dye inside the cup, and after I drop, so from that moment ahead, there will be dye in the cup. So it's a very, very basic concept and simple concept. Some fields can be represented by real numbers. In this case, they will be called scalar fields. And this is an example of a scalar field. It could be temperature, for example. And it's represented by a number. So you have your space. And in each point of space, you have the intensity of this field, which could be temperature, for example. So each point of space and time, there is an assigned number in the case of the scalar field. There is, and you can represent the scalar fields in multiple ways. For example, curves and 3D graphs, for example, if your field is in 2 dimensions. So this picture down here on the left, imagine you have a 2D space and you plot the intensity of the field in this 2D space. You require an extra dimension, so the Z dimension would be the intensity of the field. So this is a surface, represented by a surface. You can also represent in the 2D space as a heat map. So in the first picture here on the left, there is, it could be, for example, population density in a country. You can represent as a color. And you define a range of colors. This is our extra dimension. So the color is an extra dimension here. And this is the heat map. You can also use isolines and isosurfaces. People generally are used to this concept in maps. So if you are trying, you have a 2D map of some place, and you have to plot the height of some position. So you can use the isolines. and each isoline represent a height. So in this example here, this line would be, I don't know, 1,000 meters, 1,300, etc., etc. And in places where the lines are clumped, the steepness is higher, right? And in places where the lines are further apart, the steepness is lower. Okay, so if you are hiking in this mountain, you would prefer going, making a path like this instead of this, for example, okay? And in 3D, it's complicated to represent a field, a scalar field, because you require an extra dimension. So in this case, you can use isosurfaces. Here's a snapshot of a 3D simulation. And in this particular example, the field intensity is represented by the color of the isosurface. So inside here, you can see an isosurface, a yellow isosurface. Probably this is a more intense region of the field. And as you go outwards, you can see more bluish isosurfaces, which mean the field is getting lower in these regions. Okay, so these are ways you can represent a scalar field. Fields can also be, fields can also be vector fields. Let me see why it's not playing. Are you seeing the PowerPoint? For some reason, it's not playing the video. Okay, now it is. So this would be a vector field. So a vector field is represented by a list of numbers, and in this case could be used for fluid dynamics, for example. Right? So this is a very beautiful simulation of fluid dynamics. And the speed, the velocity of the field is a vector. So in each point of space and time, you have a vector assigned. Okay, so this is a vector field. Now I have a discussion for you. So first question: can you think of two examples of scalar field relevant to biology? Scalar field relevant to biology. Two examples. Once I see two examples in the chat, I will go on. Cell pressure, that's a very interesting one. Yes. Yes. Yeah, pressure is a good one. Oxygen, concentration, oxygen, right, Rebecca? Concentration of a hormone, perfect. I don't know what is a quorum factor, but I trust you. Membrane potential, interesting, yes. Potential, yes, membrane potential is a good one. Electric field is not a scalar field, Edgar. Electric field is a vector field. But then comes another question. Two examples of scalar vector fields, vector fields relevant to biology. Two examples, come on. Velocity, cell velocity, yes. It's a good one. No, diffusion is not a field. Stability is not a field. Steady state is not a field. It's something that is assigned to each point of space and time. So diffusion is not assigned to a given place or time. Diffusion is a behavior. Diffusion is yes, a behavior described by a process like the diffusion equation. Is not a field by itself. Okay. Flux, good one. Flux is a field, a vector field. Yes. Direction of cell growth. Yes, good one. Chemical potential. Potential is a scalar. Potential is a scalar. But yes, you gave good ones. I will tell you one that I think is a very important, which is polarization. Cell polarization is a very important concept in cell biology, and it has a direction. It has a intensity. So it is represented by a vector field. Okay. Now a harder question. Can you think of a different field type relevant to biology? A field type other than scalar or vector? Can you think of one? Tensors. Tensors. Very good, Jonathan. Very good. Tensor field. And can you give me two examples of tensor fields relevant to biology? Two examples of tensor fields that could be very important to biology. Stress, nice, perfect, yes. Stress can be represented as a tensor, and you can assign the stress to each point of space and each point of time as well. Other one? I asked for two. There are plenty. No, J is not a tensor, Jonathan. And it's not assigned at each point of space. It's generic. Like you don't have J for each point of space in CompuCell. But yes, it would be the contact energy matrix. Yeah, it's not a tensor. Strain, good one. Strain, yes. Strain could be a useful tensor field. Another useful tensor field could be the inertia tensor, because the inertia tensor carries the shape of the cell. So you can also ECM fiber orientation. That's a good one. Yes. So now let's talk about concentration fields. So someone said oxygen in the chat. I forgot who it was. Rebecca. Thank you, Rebecca. So oxygen can be represented as a concentration field. And concentration fields are the most talked about fields in biology. And they are represented by a scalar field because concentration is a number, okay? And we use the letter C to represent in an equation, we will use the letter C. And R here is the coordinate in space, and T is the time coordinate, okay? So some examples of concentration fields would be cytokines, oxygen, glucose, VEGF, okay? And here is how you could see a field, a scalar field in an experiment. So you can, for example, apply fluorescence to some chemical substance, and the intensity of the fluorescence is more or less proportional to the concentration of this chemical species in the space point, okay? And another discussion for us. So what would the gradient of the concentration field, would it be a field as well? Which type of field would it be? Is it a field, Steven? Is it a field? Let's start from the most basic question. Is the gradient a field? Yes. Why? Why is it a field? Different places, and also different time points, right? So as the field changes its shape in time, the gradient also changes. So yes, perfect. Vector field, it is a vector field, so gradient is a vector field. Perfect, Shelley. Derivatives are linear transformations, because derivatives are linear transformations. So because it's linear, I don't see a direct relation between being a vector and a linear transformation, but I imagine there is, because it's not a completely different concept. I mean, if you integrate all the field, it yields another object, another completely different object, right? So I mean, if the concentration is smooth enough, the derivative exists, and then it exists everywhere. Perfect, Jonathan. Yes, that's it. So gradient is a very used concept in biology, because you, for example, in osmosis, you use gradient. If some cell is secreting, how this secreted substance moves across space, the gradient is important in these cases, and it's sometimes badly understood, right? So if we have a scalar field here represented by this surface, the gradient would be this field here in the plane. So it's a vector that points towards the direction of highest slope, and the intensity of the vector, the size of the vector, is the slope itself, okay? So you can see, for example, in the corners here, where the slope is lower, the size of the vectors is smaller. The vectors are smaller. And in the intermediate region here, where we have the highest slope, you can see that the size of the vectors are larger, okay? And they point to the direction of highest increase of the field, okay? This is another image, maybe this is clearer. So in yellow here, we have the high concentration, for example, and in blue, we have the low concentration, and the arrows point, they go outwards from the low concentration region, and they point inwards to the highest concentration, right? So give me two examples of relevant gradient fields in biology. Two examples where the gradient regulates the cellular behavior. Melanie gave one, very good one. Potential is not a gradient, not a gradient of something. So in case of Lucas, the electric field, which is the gradient of the potential, this would be a relevant gradient field for biology. Okay, Lucas? Yes, perfect examples. Yes. Something, yes, osmotic pressure, yes, it's proportional to the gradient of concentration of the solute. Yes, perfect. Yes, Sharon gave a very useful example. So a chemoattractant. So some cells can spatially feel the concentration of a chemoattractant, and they sense the gradient, the average gradient in its membrane, and it can, for example, undergo chemotaxis because of this gradient. Now let's go to the concept of diffusion. So the diffusion is somewhat hard to explain, but I will explain very step by step for you. So if you are in trouble understanding, please type in the chat. I will keep an eye on the chat. So diffusion is a spontaneous process. It does not require energy. So it's a spontaneous process by which matter flows from high to low concentration regions. Or now that we know what a gradient is, it happens in the opposite direction to the gradient. So in this image here, the gradient would be pointing to the left, and the flow of the matter happens to the right, opposite to the gradient direction. So to understand how a diffusion, why a diffusion happens actually, so you have to, in my opinion, the best example is the Ehrenfest model. There's a funny music, but this is Niels Bergland fault, not mine, okay? But I will leave it mute. So in this example, what's happening? You start with a high concentration region and a low concentration region. And notice that the particles, they do not interact between them. There's no interaction. They are not repelling themselves, okay? They're not repelling themselves, but still they preferably move to the right. Okay, there are more particles going to the right than particles going to the left, simply because you have more particles on the left and less particles on the right. So it's a statistical result. It's not the result of a force, a hidden behavior. No, it's simply a statistical phenomenon, okay? So you have a region with more particles and a region with less particle. The region with more particles tend to lose particles to regions with less particles. And only by chance, there is no Newtonian or quantum mechanical forces involved, nothing. I understand it as the result of second law of thermodynamics. That's obviously, that is, could one say it's entropy? Yes, it's related to entropy, yes. So because of this statistical process, thermodynamics arises, okay? So what you know about thermodynamics is a result of this microscopic process happening in a large scale, okay? So in my opinion, there is no understanding of diffusion only from the thermodynamics point of view. You have to understand what is happening in the micro scale, because thermodynamics is a consequence of what's happening in the micro scale. And there are some situations where thermodynamics do not apply, which are very important in the field of physics. So I put a side note here, which there is a force actually, but it's not a Newtonian force, it's a generalized force. So the difference in chemical potential can be understood as a generalized force related to the number of particles. So the number of particles is changing, and the chemical potential difference can be understood as a generalized force in this case. Spatial configuration, obstacles, material types, everything can alter diffusion. So for example, if you simply have molecules spreading throughout space, you have free diffusion, there's nothing blocking, nothing consuming. You can have cells to which these chemicals attach Actually, this would be the third case, but in the second case, here you just have cells blocking the diffusion of these molecules. So you will have a less diffusion, okay? You will hinder diffusion, and you can hinder even more if these molecules can attach to the cell membrane, and it blocks the molecule diffusion even further, okay? And these molecules could also enter the cell and be broken inside the cell, be metabolized. In this case, it would not only hinder diffusion, but also take up these molecules, okay? And in the context of cellular biology, you have to understand that diffusion is a cheap process. It's a very cheap process. So whenever cells can communicate or survive via diffusion, this is a very favorable process for them. So for example, distribution of nutrients, gases, and toxins over short distances, diffusion may be the main process. On the other hand, if you want to transport nutrients from your intestine to your brain, then diffusion is not the best way, because it would take too long for nutrients to spread across your body. So diffusion is a cheap process, but it happens better in short scales, small scales. And you can also, beside the distribution of nutrients, gases, and toxins among cells, you can also have communication between cells. So some discussions here. I think the most interesting one is for single cell survivability. For single cell survivability, can you think of an example where diffusion is critical for cell survival in a single cell context? Because in multicellular context is very easy to think, because of oxygen, nutrients, etc. But for a single cell, but embryo is not a single cell, right? RNA synthesis, yes, there is diffusion happening. Passive diffusion through cell membrane, perfect. Sharon gave an extremely good example. Diffusion of metabolites, proteins, everything inside the cell, good. Actin also, right? Which is very important to build the cytoskeleton and other parts of the cell. So actin diffusion is very important. Communication chemicals between bacteria, a good one. Start with the single cell. So Edgar, I think you were trying to say then division, cell division. So during cell division, you have diffusion of certain molecules that mediate this process. Osmosis, I don't know biology. Perfect. Diffusion of ions and toxins, right? So when a bacteria, for example, releases toxins to the environment, if these toxins stay around the cell may die because it cannot access other nutrients around that are needed for its survival. So the fact that these toxins can spread through the medium is vital for the bacteria, right? and so on and so forth. There are many ways molecules can traverse a membrane, okay? So for example, it can traverse merely by diffusion. So by chance, it crosses the membrane, like oxygen. Oxygen can do this. There are also the ion channels, which allows some kinds of ions to pass and not others. And there is the facilitated diffusion. So for example, glucose is a big molecule that cannot simply cross the cell membrane. So there are these proteic spots on the cell membrane, these transmembrane proteins that help these molecules to cross the membrane. But we always model them as simple diffusion, okay? These are all diffusion. And to demonstrate that diffusion is relevant over short distances rather than long distances, there is this very funny experiment where this guy named Iberê put dye on a bottle full of water and waits until the dye stands still. So when you look at it, it seems frozen, right? It even shakes up and down, and you don't see the dye spreading. You cannot see the dye spreading. That's because even though diffusion is happening, we cannot perceive it because it happens in such a small space. We would need to look at it with a microscope to see diffusion happening. But then you can argue, well, how do we see things mixing? Well, because we mix things, we provoke advection, we provoke flow in these mixtures. And I will leave this funny face for you guys. So I hope you understand that diffusion is relevant over short distances, not long distances, okay? How about in air? So in air, there is a bunch of flow. There's a bunch of flow in air. So even much more than in liquids. So when you see news, for example, pollution spreading in the atmosphere, this is not being driven by diffusion. This is being driven by wind, okay? And well, so why do we use the diffusion equation? This would be a nice equation, right, Serena? Why do we use the diffusion equation to model this phenomenon? Well, because we think of the wind as a random perturbation, and over long time scales, we can model the wind as a random force acting over these packs of gases in the atmosphere, and we can use the diffusion equation. But we cannot escape of advection in case of winds. So people who model atmosphere also take into account the wind direction, the average wind direction. Okay, now let's jump into the diffusion equation. You don't need to know the diffusion equation, but this will appear either if you are reading a paper or writing a paper. The diffusion equation will appear. The coefficients in these equations, you need to understand what they do. So I will quickly cover these concepts with you. So here we have a time derivative, a Laplacian, which is a second space derivative, and the constant d, the diffusion, regulates how fast the diffusion happens, okay? And you can describe the diffusive process in two ways. It can be an agent-based model like the Ehrenfest model. So this is a ABM model. right? You have particles, they don't interact in this case, but they could. You are modeling space, etc. Okay. Or you can model it continuously. So in the continuous approach, we use the diffusion equation. There are other equations, but this is the useful one, okay? So the other ones are too advanced. So C is the concentration of the molecule and D is the diffusion constant. It's how fast the diffusion happens. So when you see the field spreading throughout space, how fast this field spreads across space is determined by the diffusion constant. ABM is agent-based model, agent-based model. So the agents are the molecules, for example, okay? Or could be us humans, each agent. So the overall behavior that this diffusion equation is solving is this spread behavior. So if you start with a drop of dye in the cup of water, in a very long time period, this dye will spread completely and evenly in the cup. And it does so so that the sharp peaks spread quicker than the blunt peaks. Okay, so sharp peaks and valleys flatten quicker than blunt sharp the blunt peaks and valleys. So I will run a video again. I recommend this channel so much. It has a full video on diffusion. It's called heat equation, but it's the same thing. So heat equation and diffusion equation are the same thing. Okay, so you can see that when the simulation starts, it flattens quicker because the peaks and valleys are sharper. And as they blunt, the diffusion happens slower and slower. And whenever you are modeling in a continuous model using, for example, these PDE equations, like the diffusion equation, you have to determine how the field interacts with the boundaries. So for example, in the case of the cup, I put a drop of dye here and the dye cannot go out of the cup. And there is no dye outside the cup coming in. So if I have to model the spread behavior of a drop of water inside the cup, I have to take into account how this boundary works, right? So there are many types of boundaries, but we will cover the most basic ones. So let's say I start with a drop of dye here in my system. So I put a drop of dye here. If I model the boundaries as periodic, periodic means that the edges are connected. So if the field spread through an edge, it appears in the other edge, okay? There is you can set a constant derivative to the boundaries. So for example, if you set the constant derivative in the boundaries regulates the flow in or out of the region, okay? So for example, if I set a positive constant derivative, depending on which side of the boundary I set, I could be modeling flow in or out of the region. And if I set a constant derivative equals to 0, it means that there is no field coming in or field coming out. So in the case of a drop of dye inside this cup of water, I would model the boundary, the glass, as a constant derivative equal 0. Not a periodic, because for example, if it was periodic, I would put a drop of dye here in your left, it would spread, and as it reaches this boundary, it starts appearing on this end, which doesn't make sense, right? So I wouldn't use periodic in this case. And there is also constant value. I can hold the value of the field constant in the boundary. So let's say I hold this value at 0. So it means that the concentration of the field in the boundary is 0. It's not useful in my case because although there's no dye inside the glass, the boundary does not refer to the glass. It refers to the contact between the water and the glass, okay? So, but in other situations, it could be very useful. So let's say I am modeling the heat transfer between my hand and the cup. I could say that my hand holds the temperature at 36 degrees Celsius, which in Fahrenheit, I don't care. I don't care what it is in Fahrenheit. So in Celsius, 36, I put here, my hand holds it at 36 and it diffuses inside the cup. $37. I have to test myself later. Yes, I could be sick. So to further understand the periodic boundary, there is an idea which originally I think it's from Giuliano, and Hayden made me put this GIF in my presentation. So there we go. So this is a game, it's called Asteroids, and it has periodic boundary conditions. So you see the asteroids and this, the spaceship, I don't know how it's called, but the spaceship and the asteroids, they cross the boundary and they appears at the other end. So this is an example of, very intuitive example of a periodic boundary conditions. So exercise for you guys, this I call discussion, but you have to answer. And the missiles too, yes, Sharon, well observed. Let's say you are modeling a blood vessel as a boundary to oxygen field in a tumor. So you're modeling the tumor. The tumor is your system, okay? And it makes boundary to a blood vessel with oxygen in it. How would you model the blood vessel as a boundary to the tumor in terms of the oxygen field? How would you model it? Why, Serena? Man, that is perfect. That is perfect. I love you guys. So Serena and Steven, congratulations. And it's very intuitive to think as a flow in and out, as Annie is trying to put, okay? But you have to think that the tumor growth happens at a rate too lower in comparison to the blood flow, right? So the blood flow happens so quickly that the oxygen concentration in the blood vessel stays the same, virtually the same at the scale of a tumor growth. Okay, Annie? So we are not modeling the immediate behavior in the tissue, in the interface, in the two tissues, in the tail, okay? Otherwise, you would also need to take the blood flow into account, which would make your simulation so much more complex. So congratulations, the first one. I'm happy to hear from you guys that holding concentration to some concentration, yes, this is the way to go. Let's now think of you are modeling the outer environment. No, you're not modeling the outer environment. The outer environment is the boundary to a glucose field in an epithelium. So let's say I am modeling the glucose field in my skin, and there is the outer environment here, the air. So which boundary condition would you use to model the interface between the skin and the air? Question mark. No flux, perfect, Jonathan. Yes, Sharon, perfect. That's it, no flux. So air doesn't put glucose molecules in my skin, and my skin doesn't lose glucose molecules to the medium as well. Perfect, that's it. You're going very well. Third example, a site of a tissue, a small site of a tissue where cells communicate via growth factors. And the adjacent sites have the same behavior. So you're modeling this small site of tissue. The cells communicate via growth factor. The growth factor is your field, and the adjacent sites have the same behavior. How would you model the boundaries? I want more people. Only Serena answering. Let's go. Periodic, that's it. Love it. So Gosmay, is that how I pronounce her name? Gosmay? Okay. Perfect, that's it. Periodic. And this raises a question. Does it make sense? I mean, one cell here in this boundary, it secretes a growth factor, and this cell here it's sensing at a distance. So there is a communication at a distance. Does it make sense? How would you explain that to my mother, to your mother, to your uncle? How would you explain that? Multiple cells. So it's a site, a small site. There are many cells inside this site, and the site belongs to a much larger tissue. I'll give you the answer right away. So although there is some kind of communication at a distance, yes, but why, Serena? That's the point. Why? Why is this the best approach? So I'll give you my input. So my input is, although this is not realistic, you can build a large enough system so that this site here, although it's connecting to this site here on the other side, they do not correlate. They would not correlate if they were in a closed system. So it's a first approximation of a much larger tissue, okay? But you have to be careful that your system is not so small that the entire system is communicating because of the periodic boundary conditions. These are the references in case you want to see where I took the images from, and more examples. So you are modeling a cavity. So let's say inside the stomach, and there is a gland outside your system. It is producing an enzyme, and it secretes the enzyme inside the cavity. Okay, so you are modeling the cavity. The cavity is your system, and the boundary is this gland. And the enzyme is the field. Which boundary would you choose? Constant concentration, Sharon. Continuous derivative, constant derivative. Yes, I would model as a continuous derivative, Sharon, because although you may have a very high concentration of, let's say, HCl inside the stomach, the glands do not stop producing. They do not stop producing. If it was constant concentration, the cavity would reach this constant concentration and it would hold constant. But that is not the case. The gland keeps producing enzymes. Yeah, obviously, it depends on the case, right? It depends on the case. But at a first approximation, a constant derivative, in my opinion, is a better approach. Now let's do the opposite. The cavity is the boundary, and you're modeling the gland, you're modeling the gland cells. And the gland cells produce this enzyme field. It goes out to the cavity. Yeah. Now the opposite. You're modeling the gland. The cavity is the boundary. So the gland loses enzyme to the cavity. How would you model this boundary? There you go, Sharon. That is a very good answer. Or other concentration. It could be other value other than zero. Let's say you're modeling the stomach and you know that the average concentration of HCl in stomach is X. Then you set this concentration to the boundary. And you wouldn't use a constant derivative in this case, because it would mean that the cavity is sucking enzymes out of the gland, which does not happen. Okay. And 6, a small site of epithelial cells in the gland where some of these cells secrete a specific enzyme. So it's a small site of epithelial cells in the gland, of the gland, a very small site. So the gland is very big. You're modeling a very small site of epithelial cells in the gland. Which boundary would you use? You are modeling a small site of epithelial cells in a gland. The gland is very big, and you're modeling a small site of epithelial cells in this gland. Which boundary would you pick? Periodic, right? So Lucas got right. Yes, they are producing anything. What boundary? The boundary with other sites of the same epithelial tissue. So we are already modeling the secretion of this enzyme. All right. Motieshwar. So we are already modeling the secretion of this enzyme in the cells. And the boundary, it's not a hard boundary where there is an input, output, or a fixed concentration. No, there are other cells. There are other neighboring cells, which are the same cells from inside our system. So boundary conditions is a better option for this case. Yeah, periodic. Yeah, that's right, Sharon. So if you feel you don't get these concepts, please ask me to explain again, and I'm happy to review some of them. Okay. In CompuCell, we have some diffusion solvers. So these are different methods for solving the diffusion equation in CompuCell. You can take a look at the documentation, see all their capabilities. And today we will focus on this diffusion solver FE, which models the transient diffusion. So all the diffusion process you can get from the solver. There is the steady state diffusion solver, which leads straight to the final configuration of the field, the steady state. And there is also the reaction diffusion solver FE, which allows you to model interactions between different different fields in the same simulation. So let's say you have two enzymes inside the cell, and they diffuse inside the cell, but when they overlap, they kill each other. So they break up or they generate another type of enzyme. So in this case, you would rather use the reaction diffusion solver. Is it periodic because we can assume that enzymes entering from one side of the small part of tissue and because we can assume that enzymes entering from one side of the small part of tissue are going out to the other side? So if I understood, yes, that's it. So this cell in this end are being understood as a cell outside of the system that also secretes the enzyme, and this cell here inside the system senses it. So yes, it could be understood as this. So transient diffusion means that you care about how it evolves in time. So from the initial condition to the steady state, how it develops. And on the other hand, the steady state diffusion solver gives you the answer straight to the answer, straight to the steady state with no transit. So continuous is a mathematical property. Periodic, and they are different concepts. Periodic is is related to the boundaries. So the sink cavity problem again. So yes, let's go to the sink problem again. Sink cavity. So we are modeling the gland, okay? So take a look at this image here in the top side, for example. Let's say you are modeling these 5 cells here that I'm pointing at. You're modeling these 5 cells, okay? And potentially the other cells behind them, okay? And the cavity receives the nutrient and spreads out really quickly, okay? So in this case, how would you model the boundary, the cavity as a boundary? So your cells are secreting the molecules, and the cavity behaves as a sink, okay? So they take the cavity take this enzyme and spreads evenly through the cavity. So let's say you're building this model and you know the concentration, the average concentration inside the cavity from the experiments. So you set that constant concentration as the concentration at the boundary, and you model your secreting cells normally. And returning to Muteshwar, so the number of interacting species and the spatial dynamics are not the main factor to decide upon the periodic boundary. So you are modeling the periodic boundary if your small piece of tissue, your small site, are neighbor to other sites with same behavior, same dynamics, okay? So for example, if I take this cup of water and I'm modeling the entire quantity of water inside the cup, this glass, I cannot model as a periodic boundary condition. But let's say I am modeling a very small site of water inside this cup, neighbor to other sites of water. In this case, a better approximation is the periodic boundary condition. Yes, Stephanie, yes. That's the utility. Yes, eventually I will run out of examples, as Sharon's mentioned. So, Stephanie, yes, that's the intention of the periodic boundary conditions. And you would use in other situations, for example, let's say you are modeling a tube, okay, a tube. So it's a shape closed in itself. So even this cup of water, if you, let's say this was a tissue instead of glass, it was a tissue. So if there was a cell crawling in this tissue, eventually in this direction, eventually it would come back at the same point it was. So this is a real periodic boundary condition. So let's say you are modeling a tube of cells, and there is a cell crawling, or even the other cells. The fact that it's a shape closed in itself, this is a real boundary, a periodic boundary condition. The other applications, the small site in a bigger tissue, this is an approximation. Okay, this is an approximation. It may lead you to wrong conclusions if your system is not big enough. Okay. Okay. So now I will demonstrate how to use the fields in CC3D. This is not a hands-on exercise, so you will watch me doing it, okay? How are we on time, Steph?
Yeah, so this module is normally scheduled to end at 1:15. We can go till 1:30, 1:40 or so. I do want at least 15 minutes. Let me actually take a quick second, just by a show of hands, who was interested in presenting a hackathon idea today during the extra session? You can just use your raise hand emoji. We got 2, 1. Okay. Yeah, we can go till like 1:35, Pedro.
Okay. Okay, I can do it. Yeah, perfect. Yeah, so I am opening my to edit here. And I will implement a field and you will just watch, okay? So I will generate a new simulation here. Pedro, funny. Next. I will set a small lattice so it runs faster. Okay. These boundaries doesn't matter. Okay. This is only for the cells. This is not for the field. So if you put periodic or no flux, it doesn't make a difference in the point of view of the field. So this doesn't matter. Okay. Next here, I will add a cell as a cell, doesn't matter as well. Okay, I'm just here to show you the fields. Chemical fields. Okay, let's type the name of the field, oxygen. Type the name of the field you want. Could be many fields. You can write a list of fields you want in your simulation. Here you can select your diffusion solver. I will use the diffusion solver because I'm interested in showing you the transient and how the field evolves in time. Click add and your field will appear in this list. The name and the type, the type of the diffusion solver. Next. Then here behaviors, etc. Contact volume doesn't matter as well. I'm just modeling the field. There are other options for the field, for example, secretion, but secretion is for the next lecture. So stick with us. So sometimes the Zoom bar annoys me so much I can't click on things. Okay, finish. Here's my simulation. And the steppables, nothing different in the steppables, okay? So that classic printing of useless stuff here, which I will comment out because it just slows the simulation down. And here in the XML, you can find this huge steppable called Diffusion solver FE. It carries the name of the diffusion solver you picked. Okay, so in the XML, you find these steppables with multiple coefficients and constants to set. All right. Let's say inside the diffusion solver FE, you could have multiple fields. You could have the oxygen, you could have the nutrient, you could have the toxin, you could have many types, many instances of a field here. But the instance oxygen is in diffusion solver name oxygen. So inside this section, this entire section, are all things belonging to this instance, to this field instance. Right? So here you can see the global diffusion constant. So this is the field, the diffusion constant that happens everywhere. It's assigned to all points in space. And the decay constant. I'm not covering the decay constant now. In the next section, in the next lecture, I will. So I'll comment this line. You can also set specific for each cell type, the diffusion coefficient and the decay coefficient, but I'm not using it now, so I will comment. You can set secretion inside the diffusion steppables, but I'm not using it now. Okay, so an oxygen field with a global diffusion constant, that's it. And down here, we have the boundary conditions. So it always will give you these 4 annoying boundary conditions. What I suggest you is by default, set to periodic. By default, when you build a simulation, by default, set to periodic, okay? And let's run. Let's see what we got. I use control bar. Yes, control bar. Commenting equivalent to setting to 0. Yes, yes. But depends, right, Sharon? For example, when I comment constant value here, it doesn't mean that the constant value is 0. It means that I don't have a constant value boundary. So in this case, it doesn't work like that. Okay, so here's my simulation. I may reduce the number of cells so it runs faster. Here's my simulation. And in this window, I will pause here. In this window, you are seeing the cells. So it's saying cell field here in the graphics window. You click the drop-down menu and you can view your scalar field as well. So let's click in the oxygen. Now we can see our oxygen field. And from this color scale, we can see that it's green, so my field is set to 0, so I have no field here, right? So now I will set some initial condition to our field. So in this line 58, it says initial concentration expression. I will uncomment it, and let's leave x times y, let's see what it does. Okay, so there is a problem in my simulation. The problem is that I'm not seeing this field properly. In the beginning, I may see here a little bit, but it all turns red. Why is that? So my color scale is between -10 and 10. I have to change it. To change the field visualization, you go to visualization, sorry, not visualization, you go to tools, configuration, and field tab. Okay, so in the field tab, I recommend that you unfix both min and max ranges. Okay, hit OK. It takes a while. There we go. Now we can see from the minimum value of the field to the maximum value of the field, how it behaves. And here you can see the spreading behavior. So the field spreads until it is evenly distributed. Of course, as I unfix the minimum and maximum values, I will always see the minimum and maximum value simulation. But let's say I put something in the initial condition like a Gaussian. So let's type a Gaussian here. So x squared plus y squared, and I want to center it at, let's say, 50. Yeah, there we go. So I started with a Gaussian, and it spread. Okay, until it's evenly distributed. So at zero, the intensity is 1. So let's change our field visualization to 0 and 1 to see what is really happening here. So let's fix it and put 0 and 0. No, sorry, 0 and 1. Okay. Now when we start, it's a little dot in the middle of the simulation, and it disappears. It disappears very quickly. So in the other visualization setting, I could see the field because the minimum and maximum were following the field intensity. While here I'm fixing at 1, so I don't see the field anymore. Okay, so you may face some issues when visualizing your field. Make sure your color bar is set properly. Now I will show you in 3D how to visualize a field in 3D. So let's put here Z100. And since we have another component, plus Z. So in 3D, and it crashed. Yeah, there's no time for this. There's no time for this. But I can do it without the Z component. No, at this point, this type of error would make me rebuild the simulation from scratch. Okay, just so you know how I would lead with the problem. But okay, here I'm seeing the oxygen field. Let me visualize unfixed. Yeah, it's 0 already, so let's run from the beginning. Oh yeah, that's a problem. I set here the Z dimension, which does not make sense. Yeah, there we go. Okay. So you can see that I also have these lines here. These lines, these are the isolines, which I mentioned before. So to see these isolines, each line represents a concentration. To see these isolines, you go to the same place, so tools, configuration, fields, and you can click here, so show scalar contours, and ISO values. So I can set a value myself, or simply type the number of isolines I want to see. So if I set, for example, 3 isolines, hit OK, I will see 3 isolines. So one here in the yellow, which I can barely see, one in the red and one in the green, sorry, and one in the blue. And as the field spreads, you can see that the isolines growing in radius, okay? Okay. So that's all for this presentation, this lecture. Of course, this is the step-by-step, so I encourage you to take a look at the slides. There are plenty of information here if you want to set a field by yourself. Here I explain different boundary conditions. And yes, this is an important one. So defining a linear gradient. Defining a linear gradient. But I will do it in the next session, the next lecture. We have more time. So I will begin with the constant gradient, how to set a constant gradient across space in your simulation.